Welcome back, chemistry fans. Today, we present our last lesson. This is going to be about how do we calculate voltage in the batteries that we talked about last time. So let's jump into this and let me share my screen and we will get ourselves started with our last topic. Not too challenging a topic. We've seen worse here recently, so this one should go a little bit better for us. All right, so last time we talked about how we can design these cell diagrams, how we can show what is the anode, what is the cathode. Well, now what we're going to do is we are going to try and utilize some device that I have given to you called a standard reduction potential table. And what it does is it tells what is the maximum amount of voltage that can be given or is needed for each one of these individual metals which act as electrodes. You can combine these in any fashion that you want. What you would hopefully do is take elements that are from the opposite ends of the scale and you would get the biggest amount of voltage possible. But let's say that your device, it doesn't need that much voltage. So what you would do is scale it back. And we would see somewhere in the middle is where we can get our batteries that we use. Maybe if we use copper and zinc, we could get somewhere in the 1.5 volt range, which is what we want. But if you want real power, well, then you'll see them starting to use the lithium batteries to get more and more electricity from it. If you're needing a little bit more detailed, there are tables out there that have a lot more elements on them. But what I want you to notice is on this simplified scale, it starts at the top at negatives. And I think that that's a little bit easier to remember because the negatives are always the ones that give away their electricity. They have a higher value, and negative means they're giving away this voltage. Positives tend to imply that they are going to require the electricity. They're going to take that much in. But now you'll notice on this one, they've got it reversed. So be careful how you are reading, and it's very important that you apply the positives and the negatives to what is the potential that you are trying to set up. All of this is going to be used in a very, very simple formula. The cell potential, this is the voltage, it is going to be equal to the voltage of the reduction anode minus the voltage of the oxidation. Now, we last class learned how we can utilize some of our previous skills with reduction and oxidation to figure out that the oxidation is where the anode is. That's the ones at the beginning. So what I'm trying to imply, if you just remember, the ones at the top of the scale, when they're big, large negatives, those are going to be my anodes. Let me go back and highlight that point. So up here, we're talking generally. Now, this is not always, but these could be your anodes. These would be your anodes. And more than likely down here, these are going to be your cathodes. But it's possible. It's possible we could design a battery where both of them are up here. And then we have to figure out, well, okay, the one that is larger would be my anode, and the one that is smaller valued, that would be my cathode. So they can both be negative. It just makes for something that you have to be careful with when we are trying to do our calculations for the reduction and oxidation. Generally, what happens is we always end up with a positive value because the larger number is negative. So that negative times a negative will make it into a positive. However, there are times if you use two positives, that may not work out. So be careful how you design your battery. So here is just an example of cell potential, calculating what the total volts are for this reaction. And what you'll notice is it's already done for you that there is a zinc on the left and the copper is on the right. Let's go look at the chart and see where they're getting these values for 0.76 and 0.34 from. So let's go look. Zinc has a value of negative 0.76. You're saying, wait, in the question it had it as a positive. Remember, it's times a negative to make it into a positive. And copper is down here at positive 5.2. Let's hope that those match up with what they have used here. They used 0.34. All right, well, we'll just take for their word what they have chosen for theirs. Maybe I chose copper +1. But regardless, it's always going to be the cathode minus the anode, or it's going to be the reduction minus the oxidation, however you want to word that. So this value actually started out as negative. So it's 0.34 minus a negative 0.76. That's how they got it into a positive. However you get to it, notice that the value, it is a positive value. So that means that this battery will produce 1.1 volts of energy. So let's do a couple of example problems here, and then we can turn it loose for you to try and accomplish here in just a second. Okay, so we got two example problems here to start with. We've got nickel as one of our electrodes, and we have silver as the other electrode. Now, we don't know which is the anode, which is the cathode, but we want to try and calculate then what is our, do we even worry about what the voltage is? Yeah, we're going to calculate the voltage. It may not specifically state that in the problem, but we're going to do that because otherwise we've learned something we're not practicing. So let's get this figured out. So we've got nickel and we've got silver. Let's go back to the original chart up here and see if we can find nickel and silver as far as what their charges are. Let me erase where we were. Nickel and silver is what we're looking for. So I see silver down here, and then I see nickel up here. So what we should understand from this, here is my anode, here is my cathode. This tells me that to calculate my, my overall voltage, I am going to take the anode where oxidation, here's reduction. The formula says you take reduction minus oxidation. Well, this is already a negative. So that's going to end up making that a positive. So I've got 0.8 minus a negative 0.26, meaning that my total voltage is going to be 1.06 volts. Okay, let's do the same now for the second example that I've got out here for you. Oh, and by the way, because it's positive 1.06 volts, that means then that this is spontaneous. Okay. So this battery will work. That's what spontaneous means. It's going to produce electricity. All right, so now I've got aluminum and I've got iron. Let's figure out which is which. So aluminum and iron. Let's go back to the chart and see if we have them on here. Aluminum and iron. And I have aluminum and iron is at the top. So let's see what we've got. Some of that I shouldn't have erased because it's still valid, but that's okay. We'll just leave it as is. Erase that. So I've got oxidation. So the voltage is equal to oxidation minus reduction. Oops, sorry, reduction minus oxidation. Okay, so here is aluminum and here is iron. So my aluminum is going to be a big positive value, 1.68. So it's negative 0.44 minus a negative 1.68. That's going to make that into a positive. And so my voltage ends up being 1.24 volts. That is spontaneous. Okay. So this is everything that I wish to share with you. Thank you very much for your time. Oh, one more last detail. Sorry, one more last detail. Let's do this. One more last detail. Coulomb's law. This is the essence of why this is true. The larger the charge, the more voltage we are going to get. The bigger the difference in these two charges, the more voltage we're going to get. Voltage in this case is the measure of force. So the further apart we can put these values on this chart, the bigger the voltage amount. So this is Coulomb's law. Coulomb's law in the past has talked about the closer they are, the stronger the attractive forces, the bigger the difference in their charges, the stronger their attractive forces. Well, in this case, it has to do with the voltage differences. The bigger the voltage distance, the stronger the voltage is going to be overall for this. Okay, this is everything now I wish to share with you. We have finished our whole stinking curriculum for Chemistry AP. Thank you very much for staying with me. Let's go and get prepared for a test. Thank you guys. Talk to you soon. Bye-bye.